Thank you very much. Thank you very much for the possibility to tell about the simulations, and especially focusing on the simulation of the lunar plasma environment. That is also very close to my heart. The references. So maybe I first tell what I'm not going to do. So this will not be by any means a comprehensive review of all simulation techniques, methods, or the list of all simulations that have been done to investigate lunar plasma environments. I will rather focus on, or actually I will try to introduce what you can do with different models. A little bit touch about what are the limitations. So if you really want to investigate certain physical phenomena, what approach might be most suitable. And also I will demonstrate about results, what you can do, what kind of, how you can use those simulations. And actually I will have choose those examples from our own works during the last 15 years. And as you will see, I will say several times, I will mention a model type like a hybrid model. Then I will also tell about the electrostatic particle in cell simulation, about electrostatic particle in cell simulation, magneto-hydrodynamic, some kind of combination of different models, some kind of modification of different models, and also about some waves, how you can investigate light waves or light waves into plasma. So here you can see references, and I have tried to include those references also in the plots. So the contents, because I will go very quickly this one, the moon-like interactions, because you are already now experts on this topic. But anyway, I would like to put the moon in a little bit wider context, briefly. Then actually my focus is about different simulation approaches. And I have tried to a little bit divide those different groups based on physical processes, but also the physical processes, they have a typical length scale, so a little bit also have tried to divide it by using different length scales. So I start by introducing macroscale simulations, so fluid simulations, order of 1,000 kilometers and more. Then I will zoom a little bit at smaller scale, hybrid scale, or hybrid simulations. So I will call those like a mesoscale simulations. So here we have a fluid, but here we have an ion kinetics, but electrons are fluid. But here then we zoom a little bit smaller scale and faster processes, really a full kinetic, that all of those charged particles are treated as are treated as the mass particles. So I will call in this presentation those models and those scales as a microscale process. Then you may ask that, okay, we have different space and time scales, what kind of possibilities we might have to combine and treat those at the same time. I will just bring up a couple of issues, how those might be connected, at least at a certain level. And also briefly about the waves, just very briefly. And then one concluding slide. So moon-like interaction, I will go through quite quickly because, but anyway, I would like to put this in a wider context, and in order to do that one possibility is to put those different solar system objects and the interactions between the solar system object and the sun in this kind of 2D phase space that we have here. Density of the atmosphere. The density of the atmosphere means that also there is a It also gives the density of the ionosphere because those atmospheres are in the sunlight. So here the ionosphere atmosphere density is increasing from left to right, and here intrinsic magnetic field. And actually in this seminar series, the topic is the moon, and if you think about the interaction, so we are sometimes call it like a moon-like interaction. The moon is in this origin. There is no global intrinsic magnetic field, and there is no atmosphere. There is only exosphere. And that differs from so-called Venus-like interaction, where Venus is the archetype of this one. So there is no intrinsic magnetic field, but that there is a dense atmosphere. Also, the moon and Titan belongs to this one. And then we also have a comet-like interaction, small core, but a large, extended, neutral, and expanding cloud. And then Earth-like interaction, we are not anymore in this axis. We also have intrinsic magnetic field. So we have Mercury, Earth is the more, and then giant planets, icy and gas giants. But so today we are talking about the moon-like interaction. But the moon is also example of so-called airless object. So as the name implies, so there is no air. But this kind of interaction types is the most common in our solar system because we have a lot of asteroids, small bodies. I try to put the moon at the same scale, for example, as Martian moon Phobos, or there is an asteroid. So the moon and also Mercury belongs to the same category. But at the moon, of course, it differs. If you want to simulate the moon, for example, I will discuss about the dust on moon. The gravitation here at moon, of course, it's larger than the smaller bodies. So in the simulation point of view, also you have to include gravitation if you have dust particles. But anyway, we are talking on very common general interaction type. And as we heard in the previous presentation, so this is a schematic illustration. Actually, in those schematic illustration, I used very lot of the Janet Luhmann's chapters in the Introduction to Space book. That is, it was in my reference list. So this is a little bit simplified, and the realism is not so simple. But already here we can, I would say, this illustrates something. So in the moon-like interaction, we don't have intrinsic magnetic field, but we have those local magnetic anomalies that makes the moon very interesting, special. As also the Mars has those crustal anomalies, but then there is also atmosphere and ionosphere that makes the situation more complicated. But anyway, in the first order, charged particle hit on the day side, or the face that is facing towards the solar wind flow, and then there is a vague cavity. It's not totally cavity because particles are finally filling this one. And I will come back to this one, but actually this Janet already she have made magnetic field lines, and she have drawn those field lines going through the moon, almost like a straight line, but then she have included some kind of draping here. Okay, I will come back. So it anyway means that the moon is in the first order an insulator. So those magnetic field lines are diffusing inside the moon. On the modeling point of view, I will come back to that later. It means that there is a diffusion equation, and depending on the conductivity, it tells how long it takes to magnetic field to diffuse through the moon. So there a couple of also Janet's sketch. So in the previous one, we had a moon that was a fully insulator, or almost homogeneously conducting. But you can imagine that if the moon would have a large core, for example, like this one. So in electrodynamics, that's interesting because if there is a superconducting pole, or here this magnetic field, that is caused by the surface current. It's a dipole here. But if this core is very large compared to the size of the object, you can then it might be that you can see this core, the effects of the core above the surface, because the magnetic field, they aren't like a straight line, but they are deviated. And of course, the conductivity, the time, how long it takes, it depends on the radius of the object, but also the conductivity. If you have a superconducting object, infinite large conductivity, it takes infinite time to diffuse. So it means that it doesn't diffuse inside this conducting. But if the core is smaller, it might be that you cannot see it. If this is, for example, this drawing, maybe it's 1/4, maybe, or 1/3. So in this sketch, you cannot see the creping pattern above the surface of the moon of the object. So this gives something briefly about the moon-like interactions. And maybe I will come to this one, because this is, on the simulation point of view, I will come back that also to later. So when I tell, for example, about the hybrid model simulations, so we are also modeling the interior. So we are not only modeling the region outside, but also inside. And so it means that this is a nice, I would say, combination where the plasma physics is related to the interior, and it's not the geology, it's I mean that the materials and the history of how the materials and the moon interior has developed and the properties. So the simulation approaches, maybe I will go quickly, but you may ask why to make a simulations, or it might be that it's trivial for you, but maybe I still want to point out something. So in the simulations, one way I would a little bit share the Lord Kelvin, so William Thomson's feeling that it's making simulations or the models is something that you can a little bit test how well you really understand processes and nature. So it might be that you feel that you understand, but how you can really trust that you understand. And of course, at 200 years ago, for example, mechanical models were the only possibility, but now we have computers, we can make electrical models or virtual worlds by using simulations, and we can test our ideas, how well we really believe that we understand nature. But of course, also the data analysis is one driver why to make the simulations. You really want to understand how different physical parameters are correlated each other. And a space application, if you want to build a CubeSat or some other satellites, you have to be aware about the space environment and the properties, how the space environment affects to your spacecraft. And of course, basic research, you want to understand how the nature works, processes, and how different parameters are connected to each other. And okay, why to make a self-consistent 3D model. So one reason is that the data is typically in situ. Let's say we can get the properties of electrons or ions or the magnetic field and the electric field at the point where the spacecraft is. But if we really would like to get use that information in a most effective way and get a global 3D this kind of information or knowledge about the system, and that's only possibility to really make a simulation to really see in the planet scale. And of course, in self-consistent, I will focus especially on self-consistent model. We can really see how different parameters are connected to each other. And of course, if you want to know that how the size, for example, of the moon affects its plasma environment, or how the surface material or conductivity of the moon affects, you cannot, the only way you can investigate it is by you making a simulation and change the parameters that you can change in the simulation. So what kind of equations, or covering basic equations, then are? So of course we have particles, we have a mass and field. And the particles, if we think about the role of electric field and magnetic field, then the force is the Lorentz force. So the particles are accelerated by the Lorentz force. Of course, depending on the situation, we could have collisions and also gravitation. Why then? Those are how individual particles moves. But actually, what we need to know, also to calculate, is what is the charge density. Charge density, maybe here, charge density. So then we are collecting how much we have a charge at a given volume. And then also what is the electric current density. So then we are collecting the charge, velocity, and divided by the volume inside which we have collected those particles. And the reason why we need those macroscopic parameters is that according to Maxwell 4 laws, so there are those 4 laws, the behavior of the field depends on those parameters: current density, charge density, current density, charge density. So when we really want to make a consistent model that really combines the mass to fields, so we have to derive from particles charge and current density in order that we can then see how the fields are changing in time and space. So when properties of the particles are changing, those rho and j is changing, fields are changing, and the fields are changing, electric field and magnetic field, then the Lorentz force is changing, and therefore particles are accelerated differently. So then this, in the self-consistent model, this is a feedback, particles to fields and back to fields to particles. But yeah, but that's not enough. If you know those equations, of course they are valid, or they should be, probably they are valid in the whole universe. But actually when you are using to that investigate certain physical phenomena, you have to include the information about the region, properties of the region that you are investigating. For example, if we have a Venus or the Moon, so you cannot investigate the whole space. You can only investigate a certain space region, in best case 3D box, 3D space, and then certain shape of the object. Maybe in the first order it's spherical, if that is a 3D simulation. And then you also have to have some kind of information about those initial conditions and boundary conditions, how much plasma, what happens to the plasma, that is properties of the plasma that is entering inside the box, and also what is happening to the plasma when it enters close to the object. So also then you have to include the information about the physical environment that you are investigating. Maybe I like to put those different models in a map, or this is one way how you can include different models into the map. So we have a charged particles, we have a electric field, a magnetic field, we may have neutrals, ions, electrons, maybe dust particles. And we have, roughly speaking, 2 kind of different approaches, how we can maybe treat those particles. So if we only have a couple of particles, we could, or some particles, maybe million particles, several millions of particles, we can actually follow those particles, every individual particles, into simulation. So we can actually make a single particle simulation that will really follow individual particles, and that we know the position and the velocity vector of all particles. But in reality, if we are making a global simulation, that includes, let's say, the moon. We have so many particles that we cannot follow those individual particles. So then we use a statistical approach. We are following average values. And we actually investigate, make a velocity distribution function, the probability that how much particles we have in a certain velocity range. And then we can, if we make this kind of function, we have to have rules how to develop those in times and space. And Boltzmann equation is one equation. And then we can have also the laws of equations. And then when we use those laws of equation, we can integrate over velocity space, and then we get this kind of fluid equation, maybe single fluid, magnetohydrodynamic, or multiple fluid. Actually, in this presentation, I will not touch. I don't have time to discuss about this kind of laws of modeling. And actually, to my knowledge, there is not so many laws of model simulations made for the moon. There are some, but not so many. But in presentation, I will tell about the single fluid approach, MHD, and about single particles. But not only that one. Actually, when I talk about the global simulation, I will tell about the hybrid simulations, when ions are treated as single particles, but electrons are treated as a fluid. And the name implies that is two kind of approaches. Then also I will tell about the full kinetic, that both electrons and ions are treated as particles. Maybe, yes, I think that I'm running up to maybe time, or maybe I will a little bit change I can see the clock. Okay, yes. Maybe I will go, maybe I skip this one. So just to mention that if you make a model, of course, you have to have the space, you might have atmosphere, you might have intrinsic magnetic field, you have to take into account maybe the properties of the interior. And so what kind of modeling approaches are very commonly used? One is the test particle simulation. You are really following individual particles at a given electromagnetic field. So it's not a self-consistent model. So if you want to have a self-consistent model, say the magnetohydrodynamic model is. So it's a hydrodynamic model plus J cross B force. Then the mass is treated as a fluid. And there are many different kind of MHD, ideal, non-ideal, Hull, non-Hull MHD. But anyway, it's a self-consistent model. But then there is a hybrid models that we a little bit, then the ions are macroparticles. Yes, when I say that the hybrid model ions are particles, I don't say that we have model all ions, but actually the particles are macroparticles or clouds. They are present, let's say 10 to the power of 22, 23 or so real particles. But these clouds act as a single particle because it has the same mass per charge as a single particle. And it's a self-consistent model. And then if you go to full kinetic model, as I mentioned, ions and electrons are like particles. Then there are different kind of approaches and different kind of models about this kind of full kinetic models. One is electrostatic models. As we heard in the previous presentation, there are electrostatic noise. So it might be that if you are interested about that one, you might want to use so-called electrostatic model. So here you have a time-dependent electric field, but magnetic field, it doesn't have time dependence. It only depends on space. But if you want to investigate really light waves, also, then this is the most comprehensive. You have an electromagnetic model. So both electric field and magnetic field depends both on space and on time. So a couple of examples about test particle simulations. So only maybe I have one slide. So I will show one example about how to use test particles. So one example that I will present is how the charged dust particles move near the lunar surface. For example, here you can see the density of dust particles that are injected at this point, and they are treated like test particles. You cannot see here individual particles. You can only see this kind of density, but I will come back to that later if I have time. And one classical example is so-called investigate pickup ions. So charged particles which are in the moon case produced from the lunar exosphere or emitted from the lunar surface, let's say because of the precipitating solar wind protons. And maybe I will also, this points out the kinetic nature of this space environment of the moon. So the radius is only about 1700 kilometers. So if you really have a large, massive ion, it can have a large gyro radius compared to the radius of the moon. So here there is a couple of examples depending on the mass per charge. In the Macroscale model, I will show very briefly about how equation of the Hydrodynamic model. So conservation of mass, if we don't have sinks and source, conservation of momentum. And this is like a hydrodynamic model, except that now we have here J cross B force. So here, this is the way how the hydrodynamic transforms to magnetohydrodynamic. You may ask how to get electric current. It's obtained from Ampere's law. But then you can ask that, okay, how can I get the magnetic field? The magnetic field is obtained by the Faraday's law from the electric field. It gives information about the magnetic field is propagating in time. But then you may ask how you can get the electric field. Then the electric field is get from the Ohm's law. And in this ideal MHD, it used the ideal Ohm's law, where electric field plus V cross B, where this is the bulk velocity, is 0. So, and in ideal MHD, you solve those when you also give some knowledge about what is this pressure. It might be that you assume that it's isothermal or adiabatic. So here you don't know how individual particles behaves. You have average values, charge densities, bulk velocities, pressures. And this is sometimes only possibility if you have large space regions like the sun, interior of the sun, interior of the planets, or those giant planets. In hybrid model, it's simplified in that respect that because, as I showed earlier, if you think about how electric field and magnetic field behaves, it's the Lorentz force. And ions are treated like this one. Maxwell equations actually we use only those two simplified versions, the Faraday's law and then Ampere's law. So we don't have here Maxwell addition. We don't have here the displacement current, so we don't have a light waves here. Electrons, they are treated as a fluid. In the previous slide, we show ideal MHD, but actually here we can see more comprehensive Ohm's law. Electric field plus this is important. This is an electron bulk velocity, cross B. And then there is a electric current, maybe some resistivity, and then electron pressure. So maybe just maybe mention that if we don't have a resistivity and if we don't have plasma pressure, this would be 0. And in this case, the magnetic field would be frozen to the electrons. It's not frozen to the protons, like in MHD, which doesn't have a Hall term, but this includes Hall term. Then you have pressure. Okay, pressure. Then we assume charge neutrality. Sometimes it's called like a quasi-neutral hybrid model, but briefly I just mentioned like a hybrid model. But then we assume quasi-neutrality. So we assume that the total amount of negative charge is the same as the positive charge in the analyzed grid, and then electric current. Oh yes, I have to speed up quite a lot. Then we have different numerical techniques. You can imagine that in some places you might want to get a good spatial resolution. For example, here in our model, for example, we can use a fine grid size where we want near the object, for example, and then we can split particles if we don't have enough particles. We have join if we have too many charged particles. There are many numerical techniques, but I don't have time to discuss about those ones. Then the fourth was this full kinetic simulations, and in electrostatic, it means that magnetic field doesn't have a time dependence. Once again, but now it's a full kinetic. Ions and electrons are particles accelerated by the Lorentz force. We don't have a magnetic field, but time variation. It means that the curve of the magnetic electric field is 0. It means electric field can be expressed at the potential, scalar potential, and the Poisson. Then we get the Poisson equation, and we can solve. There are many methods that you can solve this Poisson equation when you know what is the charge density. One example I will tell about is, if I have time, is the lunar surface, and how to calculate electric potential if you have a certain landscape of the lunar surface. But if you really want to investigate electromagnetic waves, then you have to use electromagnetic simulation. Once again, charged particles are moved as in Lorentz force at moon, also on gravitation. But now electric field cannot anymore presented as a scalar field. Now you are propagating magnetic field from electric field, and in electric field now you have in Maxwell equation also this displacement current, and if you a little bit reorganize this Maxwell equation, you can move your electric field to the left hand side, and here you can see that then you can propagate the electric field when you know the magnetic field and when you know electric current, and in such a way you can propagate your electric and magnetic field, and you can get, let's say, this kind of light wave. Quickly about macroscale. In macroscale, we mean that you are really simulating the whole moon region, also the wake region. In this case, you can see that here we included in our simulation such a little bit, it's not fully insulator, but those magnetic field lines, they are slightly draped, and we can play with the conductivity and get a different kind of draping pattern, or we can include a core, or actually we can include whatever 3D conductivity model inside the moon, and then we can get the more complicated draping pattern. But here you can see that anyway in our hybrid model, a sketch, it's not a sketch, it's a real simulation about the magnetic field. But then also, as we discuss about the kinetic effect charged particles, if you have, for example, mass per charge of the O+, and if you are injecting, if they are coming from the close to the surface, they have really large gyro radius compared to the moon. And one interesting topic is, of course, the tail, how long this lunar tail is and how long it is filled. And in a hybrid model, you can investigate that one. And of course, the moon is interesting in that respect that it's not always in the solar wind. It's most time in the solar wind, but here you can see, let's, for example, in a magnetohydrodynamic model, how the properties of the density is changing when the moon is moving through the bow shock in the magnetosheet in the magnetotail. So interesting thing is that it's really facing very different density values, very different solar wind velocity values, and also the temperature values when it is moving through the magnetosheet tail and to the solar wind, and also the magnetic field. Also asymmetry is associated to the interplanetary magnetic field. So you can investigate those one. And one thing, of course, is the precipitation and the space weather, because of the tidal locking, this far side and near side, they face on average different kind of solar wind properties. So here, this near side face disturbed, but this far side feels mostly undisturbed. And actually, one interesting thing is that you can actually, in kinetic model, you can actually collect how different particles are hitting to the surface, and then you can investigate what is the precipitation. For example, if we don't have a magnetosphere, actually those contours, I have included those references because I'm running out of the time. So if you don't have a magnetosphere, precipitation, it would be equal. But we have a magnetosphere, so therefore precipitation on the night side is different than the day side. And actually the average precipitation during 1 month is different. And also the energy of charged particles are different because magnetospheric plasma is different than the solar wind plasma. In mesoscale, we are now talking about kilometers to 100 kilometers scale. And lunar magnetic anomalies is one example. We have done very nice presentation about magnetic anomalies, previous one, so you have already seen this kind of drawings. This is a hybrid model simulation. You can investigate the properties of this kind of mini magnetosphere. You can also investigate what is the electric field at different altitudes and also direction of different altitudes. In microscale, we are now talking about a meter to, let's say, 1 kilometer scale, and the lunar surface is in this region. And when you want to investigate, actually it means that you are investigating debye sheet region, and then you have some of plasma coming from the solar wind, and then you have to also model fields, electric field associated to the solar wind, magnetic field, and then electric field inside the debye sheet, maybe magnetic anomalies, precipitating solar wind protons, precipitating electrons, backscattered electrons, ions, maybe some atom material, and also the sunlight that emits photoelectrons. Part of those are reflecting back. And also you could have dust particles. So this, when you want to investigate this region, that is a very also challenging and complicated. And if you put that in the map, as you have heard several times, day side is a positive, night side is a negative. You also have had in this seminar series discuss about the dust. So you know why the dust is important and critical material for both on the manned mission and non-manned mission. And actually, you can make this kind of simulation, and you can, let's say, investigate this kind of small regions, make a small particle in cell simulation, and investigate how the properties in this kind of photoelectron shield or debye shield is changing when you are changing your solar zenith angle. And you can do it by using electrostatic simulation. You can investigate how the properties, density of electrons, photoelectrons, solar wind electrons, and ions are changing. And what is the electric potential? It's actually non-monotonic potential when you move away from the surface. And also, one interesting topic is that how those landscape affects. Okay, and this is a 2D big simulation. If you have different holes, electric potential is different. If you have this kind of, let's say, moon-based electric potential is different around here. And then, as I mentioned, you can make a Monte Carlo simulation and investigate how the dust particles emitted at the different places, how the dust is changing. If you have a rover, or if you have a moon base, it's also important to know how the dust is behaving. And you may ask how to combine micro and macro. I just one slide about this one, so you have a solar wind properties. You might want to make a global model, a hybrid, by using a hybrid model that keeps the properties of the plasma near the surface. You can feed that to local 1 or 2D particle in sense simulation. You can get electric potential. Then you can include dust particles. You can use Monte Carlo simulation and investigate those dust particles. And here is one example. So here we have a dust particle emission here. We have electric shield potential, and actually now those dust, it's a quite intensive dust cloud that is formed on the around the moon. Waves, I will just mention that you want to investigate wave. Then you have light waves. You have to use this electromagnetic big model. You can see how the light waves are propagating vacuum, and then you can include the plasma, and then you can see how the plasma is changing the waves. Here you can see 1D simulations where I change the density of electrons, and you can see how it's affecting to the wavelength. And the tail, as we heard in the previous presentation, that's very interesting. There are many interesting wave phenomena happening in the tail region. And as a concluding remark, or as something remarks, I would say that the moon is a really fascinating object on the simulation point of view, because there are many time and space scales. The wake is a fascinating filling of the wake. Also, the interior is interesting, how it is in conductivity is affecting to the interaction. It's an airless object, or there is a direct surface plasma interaction. And of course, different particle species, also dust particles. And it means that for those different approaches that I presented, test particles, MHD, hybrid, and full kinetic, electrostatic, electromagnetic models, this is a very nice laboratory. So thank you